The PSpice Advanced Analysis Optimizer is a design tool for optimizing analog circuits and their behavior. It helps you modify and optimize analog designs to meet your performance goals. The optimizer lets you fine-tune designs more quickly than with traditional trial and error laboratory efforts. The optimizer can be used to find the best component or system values to help meet your desired specifications. For this circuit, we use the PSpice Advanced Analysis Optimizer to optimize the value of several of our components to meet our design goals of having a low-pass 3 dB bandwidth of a minimum of 195 MHz while having a minimum gain of 32 dB. Before running the optimizer, we must run a standard PSpice simulation and then set up measurements that will measure the goals we are trying to meet. We already have a PSpice simulation profile that will run an AC sweep on our voltage source starting at a frequency of 1 MHz, up to 600 MHz with 100 points per decibel. We'll run our standard simulation using our AC sweep profile. When the simulation is complete, the probe window is displayed. Our first goal was to have a low-pass, 3 dB bandwidth with a minimum of 195 MHz. We'll need to add a measurement for this goal. We'll select Trace, Evaluate Measurement from the probe window to open the Evaluate Measurement form. In the Evaluate Measurement form, we can select the cutoff low-pass 3 dB function. The name of our output signal was out and we'd like to measure the voltage at that output. So in the left side of the Evaluate Measurement form we will scroll down and find Vout and add it to our measurement to measure the cutoff low-pass 3 dB frequency of our Vout signal. When we select OK, the measurement spreadsheet shows our measurement and our current value of 186 MHz. Our other goal was to have a gain of at least 32 dB at our output. So we'll also add a measurement for this. We'll again select Trace, Evaluate Measurement to reopen the Evaluate Measurement form. We'll then use the max function so we can measure the maximum gain. We'd like to evaluate the measurement in decibels, so we'll pull down our functions or macros field and select Analog Operations and Functions and select the dB function which gets filled into our trace expression, and then we can then scroll down and find the voltage of our output net and insert that into our measurement, so we'll be measuring the maximum voltage at Vout in decibels, and when we select OK it is added to our measurement spreadsheet and we can see that our current gain is measured as slightly over 18 dB. Now that we can measure the specifications we're trying to meet, back in Capture, we can select PSpice Advanced Analysis Optimizer to invoke the optimizer. The parameters spreadsheet will allow us to select the parameters we'd like to optimize, so we'll click in the parameter spreadsheet and select the C3, R1, R3 and R7 resistors to optimize the values of those resistors. We multi-selected these components by holding down the Control key on our keyboard, and when we select the OK button, those parameters are added to our parameters spreadsheet. The parameters spreadsheet shows the current value in our design for each of our select components, and the optimizer will choose the optimum values for each of these components within the minimum and maximum range that we can modify in the parameters form. Next, we'll import the measurements that measured our goals from our standard PSpice simulation. We'll select Analyze, Optimizer, Import Measurements from the Optimizer text menu and select our cutoff low-pass 3 dB measurement, as well as our gain measurement from our simulation. Our goal measurements are added to the specification spreadsheet. We'd like to optimize our parameters for a low-pass cutoff frequency with a minimum of 193 MHz, and we'd also like to optimize for a minimum gain of 32 dB. Before we run our optimization, We can check the profile setting by selecting Edit, Profile Settings from the text menu. Here we see we'll be using the modified LSQ engine and will set a maximum number of optimization runs to 20. And we'll then start the optimization. After a couple of optimization runs, the tool completes, and in the parameters worksheet we can see the optimized values that have been selected for each of our components. Notice that our 7 started out with an original value of 33 ohms that has been optimized to 35.17 ohms. The resistor R3 started out at 1.1 kiloohms and has been optimized to almost 3000 ohms, and the value of R1 has been optimized from the original value of 300 to about 33 ohms. It is surely worth noting that our optimized values are not particularly practical. For instance, for R7, we couldn't purchase a 3.51739 ohm resistor. Now that we've optimized, we'll use the discrete engine of the optimizer. We'll change the engine in our profile settings by selecting Edit, Profile Settings from the text menu, and then we can set our engine to discrete. The discrete engine is used at the end of the optimization of cycle to round off component values to commercially available values. You can supply a file with your own set of discrete values or use the standard file supplied with the PSpice Advanced Analysis software. We'll use the PSpice supplied file. Notice that the discrete table column has been added to our parameter spreadsheet, and for our resistors we'll use the 5% values for resistors and the standard capacitor values that are supplied with the PSpice Advanced Analysis Simulator. We'll rerun our analysis with the discrete engine, and after a short amount of time, the optimizer supplies us with a new set of optimized values for which commercially available parts will be available. The optimizer helped optimize our analog circuit to meet our performance goals, fine-tuning our discrete component values much more quickly than could have been done with traditional trial and error laboratory efforts.